We're now at the end of a week of thinking about fluids, and we're going to add one more interesting phenomenon. We've been doing hydrostatic equilibrium for the last several lectures, ignoring the possibility that fluids might actually move. Today, we're going to let them start moving. That's the whole fascinating and complicated world of fluid dynamics. It just sounds more impressive, doesn't it? Fluid dynamics, but is in fact a very complicated subject. However, we're going to stick with some majorly simplifying assumptions here, and that's all we need for the purposes of 6C. Let's look at all of the complexity you could have in a fluid. These flow lines here could be the paths, for example, that air is taking, or maybe water in a stream. Here is actual air. These are paths of air flowing over the two surfaces of an airfoil there, i.e. a wing edge. And in the top two cases, you can see that things are fairly simple because all of these flow lines or streamlines that the fluid is going on are pretty uniform, smooth, and following each other pretty nicely. And that's all the case that we're going to be interested in today. In real life, of course, things could get much more complicated, as you can see here, because, for example, if the fluid is going very fast, then at some point these streamlines will begin to break up, and the fluid will start swirling around in circles and circles of circles called eddies. That's called turbulence. That's, as I said, that's true if the fluid starts going very fast. And another effect which is connected to this is if you cannot neglect the friction, or in other words, the viscosity of the fluid. Well, if you're used to, when we did mechanics in 6A, we usually ignored friction. And we're going to pretty much do the same thing here now that we're doing fluid mechanics and fluid dynamics. For 6C, we're going to ignore viscosity today's lecture as well. So let's just imagine that we have fluids that are all described by the upper panels A. Let's completely forget about the real world situations where in some cases the lower panel B might be a little more realistic. Whoa, is that going to be too hard to calculate? Very difficult to solve. You generally need some very sophisticated math tools and maybe a computer even to do calculations of this, or maybe just do an experiment and see what happens. So let's not worry about that. Let's go with the simple assumption here of laminar or smooth flow. That's the illustrated in A here. All right, with laminar flow, then this problem actually isn't too hard. We can handle it definitely. Let's see. Oh, here's another example. You start the water flowing out of a faucet at a fairly low velocity, and that's pretty close to laminar flow. Everything looks very smooth. All of the flow lines are parallel to each other, smoothly going. You turn the faucet up and let too much water jam through there at a fairly high speed, and it starts turning over and churning and getting really complicated. I don't think any simple mathematics is going to describe that flow of a water faucet that's really spewing out at a high rate. That's turbulent. But you could imagine that we could do some pretty good simplifications of this laminar flow that could capture most of what's going on. So let's hope that we don't have any turbulence in the situations we're going to look at. One more example here, if you want to see this happening not in a liquid, but in gas. Here is a fluid flow. This is airflow made visible by these smoke particles. This looks like some kind of incense thing. This is so zen here. And it's interesting. This is a flow which changes its character. It starts out as going roughly smooth streamlines. It starts out as pretty much a laminar flow, and then at some point it gets mixed in with some air currents that are blowing around from outside, and it goes turbulent. It transitions over. This we could describe with today's lecture. This we cannot. So let's stick with this. Laminar flow, even though you often find both in the real world. We have really only two equations that we need to know to describe the smooth laminar flow of the equations of fluid dynamics that we need. The first one is so simple that you might not even think about it, but it's basically called conservation of fluid. The fluid flows from one place to another, and then more fluid flows into the place where it was, but there are no gaps that open up. no holes or vacuum where there's an absence of fluid. In other words, every little volume of space where a fluid flows in it, an equal amount of fluid is going to flow out of it. In other words, fluid is not created or destroyed. In other words, there's a continuity of the fluid. As I said, it's really just conservation of fluid. But the continuity equation is always important. It will be satisfied, especially in a laminar flow. And you are almost always going to need to make sure that the continuity equation is obeyed when you do an actual problem on fluid dynamics. The way to think about this, I think, is a mass flow rate. That is, you'll define a point or a region or maybe a little cross-sectional area, and you'll say going through that area is a certain mass flow. What is a mass rate? It's a certain number of grams or kilograms per second of fluid which is passing through there. And as I said, since no fluid is piling up in one place, no fluid is being emptied out and evacuated, then the flow rate along a streamline has to be equal because we're not injecting or sucking out fluid here. So we have an equation of continuity which says that if you measure the mass passing through one place in a given unit of time, somewhere else along the same flow, that has to equal the mass flowing through there in that same unit of time. Or if you're talking about a fluid, for example, that has, let's suppose it's flowing through a streamline that has a cross-sectional area which varies, then we'll call the cross-sectional area A. Here's the velocity at the first point where A is measured, and here's the density of the fluid at that point. If you look at the dimensions of this, let's see, area times a velocity times a density. Well, let's see, a density times an area times a length would be a density times a volume, which would be a mass, but oops, that's a length divided by time. So this does, in fact, have the units of mass divided by time. So that is, in fact, exactly a mass flow rate there. And what the continuity equation says is if you measure this mass flow rate at one point, labeled by point position 1, it has to be equal, it's the same material is flowing through here, it has to be equal to the mass flow rate at another point. And you're going to be the one that picks the points 1 and point 2 for the particular problem you're trying to solve here. So rho AV is a constant. Rho 1 A1 V1 is equal to rho 2 A2 V2. Let's just look at this a little bit, see if this makes sense. Notice that there's a possibility now that the fluid may change not only its velocity, it also could change its density in these cases. So it's getting a little fancier. Many of the problems we were dealing with previously there, like water, for example, we pretty much ignored the possibility that the density of it could change. But in fact, we're now in fluid dynamics considering all possibilities. And you can see that if the density, for example, were to go up here for some reason, then over in location 2, something else would have to go down here in order to compensate to keep the mass flow rate constant. So, for example, you could have a kind of a bottleneck here where the velocity slowed down. Suppose V2 is less than V1. But then rho 2, and we keep the area the same, it's just like a uniform cross-section pipe that just has constant area, A1 is equal to A2. If we make V2 less, then rho 2 is going to have to build up to exactly compensate. Things, just a bunch of people going through a station and they slow down, or cars on a freeway, they slow down at some point, then there's going to be a higher density of cars there. Of course, there's also conservation of cars on the 405 freeway as well. So that's not a bad analogy. And it's not too turbulent either. All right, that's our general equation. Let's see if we can apply this to some specific real-world problems that I might give you on the exam. Oh, this is an interesting one because it's based on blood flow in the human body, which is actually a bit more complicated than this because there is a lot of viscosity. In other words, there's a lot of friction, which you'll see at the bottom here. I'm going to completely ignore that for right now. So ignoring that, we can solve this problem by only using the equation of continuity. Let's see, in humans, the blood flows from the heart into the aorta, and then it goes into big arteries, and then little arteries, and around, and then in capillaries, and squishes through that. And so that's fine. It starts out then, almost all, I guess, all of it is going through this very big pipe here called the aorta, and the radius of that is 1.2 centimeters. And the blood is flowing through there. You can measure this pretty well. Is about 40 centimeters per second. Now, all of that blood then has to get divided out. It all goes through the aorta, but it all gets split up into many smaller arteries, which then split into smaller and smaller and smaller arteries. And by the time it splits down into capillaries, the capillaries are much smaller. But there are, of course, many of them. The blood flow has branched out, hasn't it? So typical capillary, I didn't know this number, darn, is that small. That's a radius of only 4 times 10 to the minus 4 centimeters. And the blood has really slowed down there also. Now it's just going at 5 times 10 to the minus 4 meters per second instead of 40 centimeters per second. Oops, we've got some different units. We better keep track of those units here. All right, from that information alone, if we ignore viscosity and we just use the continuity requirement, then we could work out how many capillaries there are in your body, basically by the formula conservation of blood here. So our conservation law, then, since we're not going to change the density of the blood, we're only going to change the number of different little pipes that's going on. We start with one pipe here. So at the beginning, N is 1, and then at the end, when it's going through the capillaries, N is probably a huge number. Now, we have to multiply times the area, and then we also have to multiply times the volume. We've been given this information at 2 locations, right? We've been given the area when all the blood in your whole body is going through the aorta. So what's the area of the aorta? It's pi r squared. So let's see, that's pi times 1.2 centimeters squared. And then we're also given the velocity at that point, which is 40 centimeters per second. Looks like we're doing this all in centimeter units. All right, so that's the way I left off the pi there. That's okay, because the pi is going to also cancel out the pi that's on the other side of the equation. So here's your rho AV, or your NAV, leaving the aorta. By continuity, it must equal the NAV when the blood is all dispersed going through n number of capillaries. At that point, each capillary only has a cross-sectional area, pi r squared, so that's 410 to the minus 4 squared. Ooh, that's going to be a much smaller number, and it's going very slowly. The velocity has dropped way down here. Let's see, whoa, 5 times 10 to the minus 4, that wants to be centimeters per second, by the way. All right, so I made a mistake there. Let's suppose that this was given to you in centimeters per second. There, I'm going to fix that. All right, then let's just move all of these numbers, these little numbers over on, divide through on both sides, and we'll get n on this side. Let's see, I have 40 here, and then there's, I don't know, 10 to the minus 7. Over here becomes 10 to the plus 7. And there's another factor of 3. It's like 10 to the 10. Wow. N turns out to be something like 7 times 10 to the 9. 7 billion capillaries. That's like 1 capillary for every person on the planet right now. Darn. All right, I'm not going to go in there and start cutting you up and looking at your capillaries, but if these numbers are approximately correct, which I think they're fairly realistic, your blood is going through a ton of capillaries so that every cell in your body can get a chance to get some oxygen and get rid of its waste. Amazing system, isn't it? Just incredible. All right, if you don't like biological systems, I can give you some other problems, for example, with airflow. Air, of course, could be compressed, it could get denser or less dense, but we're going to ignore that right here. So we'll assume the air density is a constant in this simple problem here. Airflow through ducts. That's a classic Physics 6C problem. So we have a duct here of an air conditioner where the air comes in through a rather small cross-sectional area. That's the opening of the air vent into the room. It comes in at velocity v1. So we know that rho 1 v1 a1 has to be the same as what? The air flowing across this much larger room. It's going to go all the way across the room. Okay, I know this isn't going to be perfectly laminar flow, but we're ignoring that. We'll assume continuity holds here. So rho 1 v1 a1 has to equal, going through the room here, rho 2 a2 v2, and we're assuming that rho 1 is equal to row 2. So basically, A1V1 has to equal, AV is a constant, so A1V1 has to equal A2V2. So you ought to be able to figure out, it looks like, in other words, the air is going to slow down as it gets into the, well, let's see, actually, we're given that information here. The area, the air comes into the room at 3 meters per second. All right, so that is V1 there. And then, let's see, actually we're given a flow rate, sorry, you have to look at this problem carefully. We're given, it's the first time I looked at it, a long time here. We're given a flow rate of the air when it hits this much larger room here. We're given the flow rate, but you have to understand what the flow rate is. It's given to you in a backhanded way. It says that the flow rate is such that the air can completely replenish this entire volume of the room in 15 minutes. All right, or what is that? 900 seconds. Okay, so the air can go all the way across here in 900 seconds. So the flow rate then wants to be AV coming in from the air duct here wants to be the flow rate in cubic meters per second, 300 cubic meters divided by 900 seconds, which is, what is that? That's about 300 divided by 900 is about 1/3. So if AV is 1/3, then V coming into the room was 3. And so we're trying to figure out here actually what A1 is. Well, if this is 3 and this has to, the product of AV has to be 1/3, then A1 has to be 1/9. And 1/9 of a square meter is 0.11 square meters. So that tells you how big the duct has to be if the air is coming in at 3 meters per second. So you see, in every one of these problems, there may be, in this problem, for example, there were 4 variables, and 3 of them were given to you if you work through them properly, and then you're able to work out what the one unknown is, A1 here. All right, so that's just coming from continuity. I haven't done anything very fancy yet. Now, there's one other thing that needs to be conserved aside from conservation of total fluid, and this is the important one. This is Bernoulli's equation. This is kind of the money equation for this lecture here. When, for example, the fluid speeds up or when it slows down, some force, some work had to make it go faster or slower. So it was either pushing on, it was either doing work on something else or work was being done on it. Well, how could that happen? One way, for example, is that the pressure could have changed, because a pressure pushing something over a certain distance corresponds to a certain amount of work that's been put into the fluid, meaning that you would expect it would acquire more energy. Now, the opposite situation can occur, for example, if the fluid goes to a greater elevation, if it has to go uphill, for example. Then it's losing gravitational potential energy, which of course is mgh. So what Bernoulli's equation says, it's just a conservation of energy equation for a packet of fluid, a little pink disc or cylinder of fluid that might be changing its speed, it might be changing its density, it might be changing its height, but whatever all those changes are, the work that is done on that fluid has to equal its change in total energy. Its change in total energy is the change in its kinetic and its potential energy. Does this sound like 6a? It's basically just 6a applied to this moving fluid packet. Now, in general, this is a fairly complicated equation. It's all bookkeeping. There's a lot of terms that you might have to keep track of, unless some of them simplify in the problem that I'm going to give you on an exam. So, for example, what is this actually saying? This is measuring, I kind of like the beige version of this formula. It just makes more sense to me. Let's look at the beige version here. At one point down here, point 1 here, the disk is going through a cross-section A1 under pressure P1, and it has a, we're going to ignore density changing, it looks like, in this particular, well, formula, but that really should be a row 1 also. And it's going to a certain velocity v1, and it's at a certain height y1. So there's the pressure, the kinetic energy, and the gravitational potential energy. Well, the change in pressure here is equal to the change in kinetic energy plus gravitational potential energy. So this is, as I said, in general, there's a lot of things to keep track of, but in one of the problems, I'll give you enough information so you can work out all of these, so you'll know all of these, and then you have to work out one. That's what I'll ask you. All right, so that looks like a fairly complicated formula. I don't expect you to derive the formula. I just want you to have an appreciation, understand this is just energy conservation. If you if you increase the pressure on something, then you've done some work on it. If you decrease the pressure, it's lost some energy. So let's look at a specific example so we can understand how Bernoulli's equation actually works, or Bernoulli's law. All right, what is one of the consequences of Bernoulli's law? Think about this. When the velocity of a fluid is high, that's the kinetic energy is high. If we didn't change anything else, let's go back and look at our formula. Let's see. I'll go back and look at the formula here. So for right now, I'm going to have it in a horizontal pipe. So y1 and y2 are equal, so that term doesn't change. So you can subtract it off of both sides. But notice what this is saying. If there's a region where the velocity is high, then that's going to correspond to a lower pressure than the pressure in the second region where the velocity is low, where this term is smaller, has to be compensated by this term being higher. Do you see that? If I'm ignoring any change in the gravitational potential energy, it just has to be a change in the kinetic energy of the fluid. Now this should make some sense. So look at this again. If the fluid has a high velocity at some point, it's going to have a lower pressure. And that's because some work was required, basically higher pressure, to make it accelerate, to make it go faster in the first place. Let's look at water pipes. This is a classic problem. Love to ask these problems. Actually, they seem to love to ask these problems on the MCAT as well. This is your classic. It could be blood flowing through arteries, but you get tired of doing those questions. So we're just going to have hot water going through pipes in the house right now. Let's see what all the information is we're given here. This is a little bit of a complicated problem. It has several things going on. Let's see if we can keep track of all of them. The water comes in initially through a 4-centimeter pipe. So we know the cross-sectional area of that is pi 4 squared. Square centimeters. Oh, sorry, 2 is the radius, so pi 2 squared square centimeters. And it's coming in at a velocity 0.5 meters per second. And the pressure is 3 atmospheres. You remember that's 300,000 pascals, pretty much. All right, now it goes, several things happen to it at the second point that we're measuring things. Of course, energy has to be conserved. So we know P plus rho GH plus rho V squared. Now, we have to measure that again upstairs. It's now on the second floor, so it's gained 5 meters in elevation. That's a significant amount of gravitational potential energy that the fluid, the water has gained going upstairs. It's now going through, just to make everything completely complicated here, all of that water that was going through a 4-centimeter pipe is now going through a 2.6-centimeter pipe up in the bathroom there at your sink. And the pipe doesn't divide, so we also have continuity happening here. And we want to find out what else happens. In other words, how much pressure, for example, is there going to be in the upstairs bathroom when it comes out of the spigot? It started out at 3 atmospheres, which is quite a lot of pressure downstairs. But now the question is, what's the pressure going to be upstairs? First, before you can solve this at all, you need to get the continuity equation solved. That's your first step in this. If you can't solve that, you really won't be able to solve the rest of the problem. That's okay. Continuity, pretty simple here. Well, let's see. Gosh, I was really lazy. I just did pi d squared, which is area, times v is equal to pi v2 squared. Sorry, pi a2 v2. Sorry, not pi. What I did is I just said, since there's one pipe going to one pipe, I said that the area times the velocity is equal to the area times the velocity upstairs. I canceled out the pi's, and I was so lazy I just put in the diameters. Okay, yeah, I realized that actually these should be radii here, so those should both be divided by 2. Well, so what? Because these are also diameters, so they should both be divided by 2. The proportions that I've set up are correct. So let's see, what is this? Well, you can read it. 16.8 over here divided by, what is that squared? That's about 6. Anyway, so the velocity upstairs is indeed faster than the velocity downstairs because we have to jam all of that water through a smaller pipe. And so to obey continuity, looks like the pipe has basically only about half as much cross-sectional area, so it has to be going a bit more than twice as fast as it was downstairs. So by the time it comes out the little smaller pipe upstairs, it's going now at 1.2 meters per second. Aha, it's gained kinetic energy. How much kinetic energy has it gained?